Everyone, and welcome to the first lesson in Activity 1. Today we are going to be talking all about expressions, writing them for a sequence, and using different notations, particularly subscript notation, to represent our sequences. So if you look on the first page, on page 3 here, with our notes, we see here this table talking about Bopper's DVD store. And basically what happens is each time you rent a DVD from the store, a little outdated here, right? You get points towards eventually a free rental. So if you have one rental, you have 3 points. And then for everyone after that, you get 2 more points. So on rental number 2, you would add 2 points to your total. You'd have 5 points. After your third rental, you'd have 7 points because we're adding 2 more. Then we'd have 9 points, 11 points, and 13 points. So this table up above is kind of showing us those things. And each of them then, if we are looking here, what our terms are in this overall sequence, we would have term 1 is 3, term 2 is 5, term 3 is 7. Okay. Now, that leads us into a very important little section here in the middle of the page that talks about notation. That Bopper's sequence, B sub n, right, is the big name of it, is standing for our sequence as a whole, right? And we have some subscript notation that can then describe each of these in the sequence as well. So again, if we start listing out our sequence, 3, 5, 7, 9, 11, 13, 15, and 17, our first H terms. As a whole, again, we would call this sequence B sub n. Sometimes they use the brackets around it to just denote that it's the whole sequence. Sometimes you'll see it just represented without the brackets as well. Now, normally what we do is we use lowercase b to represent then each of these terms. Okay, so for instance, this is B sub 1, this is B sub 2, the first term, the second term, the third term. And if we are just talking about a general term in this sequence, it would be our lowercase b sub n, meaning just term number, whatever n is. Okay, n is representative of what term number we are talking about. So if they ask us for the meaning of our 7th term, B sub 7, our 7th term this time would be the number 15, because that is the 7th term in our sequence. Now, if we want to look for an algebraic expression to represent this, notice our pattern each time is that we were adding 2, right? We notice we're adding 2 points each time. However, if I just took my term number and added 2, for instance, my first term 1 plus 2 is in fact 3, so that checked out. But if I tried to do my second term, so like 2 plus 2, that didn't equal 5, like we know it should up above. It only equaled 4. Okay, so what we're going to notice instead, though, is if we change around and instead of trying that, if we make this 2 times n plus 1, what this will allow us to do is get our algebraic expression, because we can say, okay, 2 times my first term 1 plus 1 is 3. 2 times n of 2, second term, is 5. And it's going to keep working for our different patterns. So we could say the general rule to find our term this time is 2n plus 1 would be the rule. Now, again, if we're looking at this in the context of this situation, n is our term number, but in this case, for the sake of the problem, n is the number of DVD rentals. So a little bit different in the context of the problem. And then, and again, this time we would say that it's 2 times your number of rentals plus 1 would give you your total points if we're comparing this then up to this expression. All right, now take a time out for a second to flip the page and continue on to look here at our different rentals based on this picture here, right? So what we notice is we start graphing these points. So plot the points now. We see that after one rental, we had 3 points, 2 rentals, 5 points, 3 rentals, 7 points. We see those points plotted. Now, if we look at this to analyze, what are some things that would make our graph a function of n? Well, first of all, it passes the vertical line test. It's 1-to-1. For every one of our n values, there is only one output value we have. And in this case, we see the points there. Another way that would make this a function is, if another way of saying that with the vertical line test is that each one had that unique piece there. We didn't have any overlap on that. Now, if we look down the next part for part C, what are some properties of the graph, again, that makes this possible, that these are on a line? These are what we call collinear. In particular, they are on the line 2n plus 1, or I think 2x plus 1 for your algebra days. Now, something interesting to note about this is that we have discrete points on this. Now, what is discrete data? Well, discrete means it's not continuous. For instance, there's no such thing on here as having 3.5 rentals. You're either going to have 1 DVD rental, 2 DVD rentals, 3 DVD rentals. There's no such thing as a 0.5. So that's why we don't have a line to connect this, because we just have these data points. There isn't anything connecting in between here because officially those don't exist. Now that leads us down to question number 5. How many DVD rentals are needed to obtain a free rental? Well, we talked about before, we need 24 rentals in order to do this. So what we could do is set our expression 2n plus 1 equal to 24 to see when we are going to hit those 24 points. So if we subtract and we divide then by 2 to get n by itself, we notice it comes out to 11.5. Now, relating this back to what I talked about up above, there is no such thing as having 11.5 rentals, right? So really, for the context of this problem, we would need to round it up to be a total of 12 rentals because, again, there's no such thing in this case as a half a rental. Once you hit the 12th rental, that's really when you're going to get it free on this particular problem. Now notice on this next problem, we have, again, another sequence. This time, what we are noticing is that we are adding 7 each time. And again, we want to write an expression to be able to actually find every term in this sequence. So again, it's not so simple as saying, oh, I'm going to just take the number 1 and I'm going to add 7 each time, and then I'm going to take the number 2 and add 7 each time. What we notice when it comes to these patterns is that we need to kind of play around. And what this first number actually ends up being with our expressions is the value that we are increasing or decreasing by. In this case, we are adding 7 each time. Okay, so if I play around with this, 7 times 1 is 7. I need it to equal 1 to start, though. So I actually would have to subtract away 6 to get my first term of 1. Now, if I try that for the second piece in the pattern, my second term, so 7 times 2 is 14. If I subtract away 6 from that, I get 8, which is the second term. And then same thing here from term number 3. 21 minus 6 is 15. So it's working out that if I take 7n and subtract away 6 each time, I can get my expression. So it turns into basically a little bit of guess and check to find that. Now, the nice thing is, once you have this formula, you are able to use it to then quickly find different terms. So for instance, without calculating the first 29 terms, I can plug in and find term number 30 by just plugging 30 in for n into our expression here. So 7 times 30 minus 6 is 204. All right, our next one then we have here is asking us then, similar to what we did with the DVDs, is to work backwards to figure out what term number is 148. So a sub n is 148. We know that the first term in this, and we know that this is 7n minus 6. We're trying to figure out what term number is this. So again, if we add 6 to both sides so that we get 154, and then that's going to equal 7n, divide by 7, and this is going to come out to be term number 22. All right, now there is one on number 7 for you to try. Okay, notice this, what the pattern is. First of all, how much are we increasing or decreasing by each time? And then try to find yourself what is the algebraic expression, what would be the rule for this. All right, now going back to a little bit more then with terminology, notice we call a sub 1, that means your first term, right? So if they're telling us the first term is 5, notice this next part is asking us to talk about, okay, what would my next term be if I was adding 8 to my term each time? So take a moment to write this down. Think about this like our current term. And then from there, we have a sub n plus 1. That would mean the next term. So what they're telling us in this subscript notation is that our first term is 5. And then what we're going to do to find our next term is we are going to end up adding 8 to that to find our next term each time. And then you take that previous term and you add 8. And you take that previous term and you add 8 so that our terms end up being 13, 21, 29, and 37. So a little bit more with using that subscript notation to find our rule. Okay, now all of these patterns are what we would call an arithmetic sequence, right? And with these arithmetic sequences, we notice that we are either adding or subtracting each time. Not every sequence is going to be that pattern of just adding or subtracting. So we had our original rentals. They're calling this pattern P sub n now. And then they're saying, okay, what if you also had a different place that said, okay, you earn a different amount of points, right, each time that you earn this. So like for one rental, you're earning 3 points. For your second rental, you're earning 5 points. So after rental number 1, this is 3 points. Rental number 2, then you had 3 points and now another 5 points. Your total points are 8 in this sequence. And then if I make DVD rental number 7, add 7 more to my total points, I have 15 in the bank. Add 9 more on, 24. Add 11 here after rental number 5. Add 6 more after rental, 13 more after rental number 6. So we see this pattern. Now notice on this one, okay, P sub n, this first one has that same pattern that we were noticing in the beginning with the boppers, where we are increasing by 2 each time. And there's this nice general rule that it's basically all of our odd numbers. Okay. However, to get our second sequence here, this is not going up by a consistent value each time. It went up by 5, but then it went up by 7. It's not going up by a nice consistent number each time. So what we're doing is we're adding the current point total to our previous balance. So to our previous balance. So to get this sum each time, again, it's requiring you to add different numbers together each time. So what that would look like with, again, our notation, if we skip down to part E, is that we would be adding to get our next term, so plus 1, we're taking our current term and adding the point total from the other sequence, right? And officially, it's kind of that next point sequence. So think about, to get this number here, we had to take our previous balance and add the piece of n plus 1. So using that subscript notation to show this, okay? Now, this is a little bit different than our last ones, right? Because what's happening is, if we look at this data and start plotting these points, it doesn't, our fantastic flicks, the points go up nice and linear again, but then the actual total amount of points earned is no longer that nice, pretty linear data. So just because there's a pattern there to that sequence doesn't necessarily mean that this sequence is going to continue to be that nice line that we saw before in our previous examples, right? So this time it's still discrete data, but it's not going to have that nice linear piece to it, okay? So to summarize some pieces today, okay? Again, we talked about sequences in general, and our sequences in general, just a list of numbers or items we see, okay? There's usually some sort of pattern to them, and in particular, when we have an arithmetic sequence, this is when we have them that they are being either adding, or subtracting a consistent value, okay, with these. So adding or subtracting, again, think linear shape to our graphs. Right? We will work much more with both sequences and specifically arithmetic sequences in class. Thanks for watching.